So thanks a lot to the organizers for putting this workshop together. Not having old people is a particularly nice kind of idea, but I am wondering, you know, until what time can we be counted as young? So maybe there should be some kind of running test, you know, 100 meters in under 12 seconds or so. So okay, so today I'm going to be talking about many-body localization and periodically driven systems, and I will present a couple of results. So first I will try to give you a feel for what this many-body localized phase is like, and I will focus on the properties of the eigenstate and on the dynamics. And so in particular, I will show that in some sense this phase is integrable, right? And from this integrability, we will derive the understanding of universal dynamics in this phase. Then I will switch gears a little bit and talk about periodically driven many-body systems. So Mark yesterday talked about topological phenomena in periodically driven single particle systems. So here I will tell you some results about driven many-body systems. So in particular, I will show that if you drive a many-body localized system, it can stay localized. And second, I will derive a general upper bound on the heating rates in periodically driven lattice systems. And we will see that this bound is actually quite strong. So it is exponential in frequency bound. This work, so first part was done with Zlatko Papic, who used to be a postdoc at Perimeter, and now he is faculty at University of Leeds, and Max Serbin, who was a grad student at MIT, and now he's a postdoc at Berkeley. And the second part was largely done with these two gentlemen. So Francois is in Paris, and Wojciech is in Leuven in Belgium. So, you know, when you read the statistical mechanics textbooks, right, it always starts from the concept of ergodicity, right? So ergodicity, it's a postulate, right, which tells you that a system, as it evolves, it would explore full allowed phase space, right? And really, it is from this postulate that you derive most of the things in statistical mechanics. And so thinking about classical systems, there are of course examples of systems which are ergodic. So these are the ones which have chaotic dynamics, right? So and a simple example is this stadium billiard, right? So you take a billiard, you launch a particle, and then as you wait, it will cover the full phase space. Because its motion is chaotic. Now, there are also important exceptions. Classical systems which are not ergodic. Those are the ones which are integrable, which have a lot of conservation laws, usually due to symmetries. And the simple example is, you know, if you change the shape of this billiard and make it elliptical, right? So the motion in this system is no longer ergodic. Now, our goal is to understand ergodicity and its breakdown in quantum many-body systems. So, but before we start talking about ergodicity breaking, so let me briefly tell you what people mean by ergodicity in a many-body system. So, setup is quite simple. So let's consider some, for example, interacting spin system, and let's prepare it in some initial state, right? So for example, it could be a simple non-entangled product state where spins are just pointing up and down randomly. And then you evolve it with the system's Hamiltonian, right, for some time. So it turns out that there are systems in which any subsystem would appear to be thermal after sufficiently long time. And this is a little bit surprising because the system as a whole is still in a pure state. right? So, but the intuition is that, you know, this subsystem can interact with the rest, and this rest acts as a heat bath, right, or as a reservoir. So, what about microscopic understanding of thermalization? Thermalization and ergodicity. So such systems where parts thermalize are called ergodic. So what about microscopic origin of thermalization in these systems? So there is a strong conjecture called the Eigenstate Thermalization hypothesis, which essentially states that in ergodic systems, even individual many-body eigenstates would appear thermal, right? So if you look at some eigenstate and measure local observables, they would be the same as microcanonical ensemble. And from this statement, you can derive that for physical initial states, your system would thermalize. And so this conjecture is generally unproven, but it's been tested on particular examples, and it works nicely. Now, question we would like to ask: so are all many-body systems ergodic, right? So if you have a many-body system with generic interactions, does it have to be ergodic? And the answer is no. And let me explain how that happens. How can a system avoid ergodicity? So as you will see in a second, really the central phenomenon is that of Anderson localization, right? So Tobias introduced it very nicely. So essentially, essence of Anderson localization is that a particle, that disorder can localize a particle in some region of space, and it's stuck there forever, right? So you can already sense that this is some this might be a route to ergodicity breaking, right? So now, natural question to ask: if we start, let's say we start from an Anderson localized system and we add interactions, right? So can localization exist still in the presence of interactions? And so, there has been a lot of progress in answering this old and difficult question, both using perturbation theory, starting from these two papers, and numerically. And so, and the answer that emerged is that yes, indeed, many-body localization is possible, right? So in fact, in systems with short-range interactions, it is inevitable if disorder is strong enough. Okay, and therefore, we have this new phase. The most interesting feature of which is that it is non-ergodic, right? So dynamics in this phase is not described by statistical mechanics, right? So if you repeat this quench experiment that I described, so you just prepare the system in some state and trace its evolution, it would do something else. It would not thermalize, and we would see what it does, right? So in the first part of the talk, so I will show to you that this phase is in fact integrable, right? And it's integrable in a very strong sense, and then from that we would derive dynamical properties and would see that they're non-trivial. So it was already, I guess, clear from the previous talk, but so part of the excitement in these questions comes from experimental progress, right? So there are various kinds of artificial many-body systems, right? Most notably called atoms and optical lattices, which are very tunable and rather well isolated from the environment, right? So, and here in the systems you can engineer disorder, you can tune interactions, right? So they're very well suited for studying thermalization, ergodicity, and many-body localization. And so, while experiments on non-interacting Anderson localization have been around for some time, so very recently experiments on localization in interacting systems started appearing. Right, so in particular, there was a recent experiment from Bloch group where they observed some signatures of many-body localization in a one-dimensional optical lattice. So I won't go into details, but the main point is that studying this phenomena is now experimentally within reach. So in what I'll talk about, so I will use entanglement entropy, and so let me just give you a very brief reminder what it is, especially since we have experimentalists in the audience. So let's consider some many-body system and some pure many-body state of this system, and let's just ask how quantum is the state, right? So how non-classical is it? And the way to quantify it is the following. So you can ask, okay, so if I just keep measuring left part of the system, right, how many different outcomes can I get? And if the system is entangled, right, then you can get many different outcomes. And the way to quantify it is just you can write down the reduced density matrix of the left part by just tracing out degrees of freedom on the right, and generally you would get a mixed reduced density matrix, even though you started from a pure state initially. And then, in order to quantify how mixed it is, you can just use usual von Neumann entropy, right? So just trace rho log rho. And this is called the entanglement entropy of state psi. And this is a measure, so you can think of this as a measure of quantumness. And recently it's emerged as a very useful tool for characterizing and classifying quantum order and ground states, right? So various topological phenomena. But you will see in a second that it's also a very useful quantity when you think about quantum dynamics and highly excited states. Okay? So simple model of many-body localization. Let's consider spinless interacting fermions, which are hopping in a 1D disordered lattice, right? So you have, on-site energy is random, you have nearest neighbor hopping and next nearest neighbor interactions. This model has representation in terms of spins, so by Jordan-Wigner, you can map it onto random field XXZ spin 1/2 chain, right? So you just have XXZ chain, and you add random field along Z direction on each side independently, right? So and you draw these random fields from some distribution, right? Which would characterize the strength of your disorder. Now, so this model is nice because it's simple and one-dimensional, so you can study it numerically, and from numerics, there are several works from which we know that this model shows many-body localization as strong disorder. And then at weaker disorder, it undergoes a transition into the ergodic phase. Yeah.
So, if you study now, for instance, entanglement entropy, this model, does it play any role that the Jordan distribution is non-homogeneous because of the disorder?
No. So I don't have it on top of my head, but it doesn't make a difference. But for simplicity, you can no. Here it would not enter, right? It would not enter, so that's not a problem. Yes. Right. So usually what people do just study this spin model, right? But it does make a difference. So let me start by telling you about a numerical experiment that these two papers did, right? So essentially they exactly numerically studied the setup I described. So you prepare a system in some simple classical state, which is a product state of all spins, and then you study its evolution with a localized Hamiltonian, and you ask what happened to the system. And so, turned out that the most interesting things happen in entanglement, right? So you just essentially measure how entanglement grows as a function of time. And here is what they found. So you just plot entanglement as a function of time. You start at 0 because it's a classical state. So first of all, if you turn off interactions, things are boring because entanglement grows just a little bit, and this growth is just because localization length is finite and spins near the boundary can hop by the localization length, and then it saturates at a value which is independent of the system size, right? So all the action is at the boundary, it's nothing special. However, so as soon as you turn on interactions and go into many-body localized phase, things become very puzzling because so what you find is that entanglement keeps growing as logarithm of time for many decades in time, right? Even if interactions are weak, right? So you see this beautiful log over up to times which are 10 to the 10, right? Very long times, and these systems are short, right? But what is more surprising is that so you have presumably a localized system, right? So but still degrees of freedom far away have a way of communicating, right? So information does spread, even though charge and energy don't, right? So yeah, what is important also is that if you look at the saturated value of entanglement, it is actually extensive in the system size, right? So, and this is what tells you that even the most remote spins eventually learn about each other and get entangled, right? So this was a puzzle, and originally, so this paper somehow conjectured that there is still very slow equilibration due to rare, very slow processes, right? Things maybe still move, but exponentially slowly. So, but turns out this is not the case, and so I'm going to explain to you what happens in reality, and but more importantly, so thinking about entanglement and explaining it, so it served as an inspiration for understanding the phase better, right? So in fact, so let me first talk about integrability, and then once we see that the systems are integrable, we will get this log growth of entanglement as a simple implication. Yeah.
So I looked at the y-axis of the entanglement.
Uh-huh.
And it doesn't really grow that much, right? It went from 0.25 to 0.5. How should I interpret this number? Because it looks like it's just not a big deal, right?
Well, I mean, big deal or not big deal, the effect is very clear and very strong, right? So it's a number. You're right. So you should interpret it as follows: so that entanglement becomes extensive in system size, but it is subthermal. You should interpret it the way that system does not fully thermalize, right? But this is just a matter of parameters. So here disorder was very strong, right? You can, if you play with it, you find that that this value, of course, depends on disorder. So if you make disorder weaker, right, then you can make this number large, right? So, but that's a good question, and the short answer is that this number tells you that system does not really thermalize, right? This is some other kind of entanglement, not the kind where everybody gets entangled with everyone and system is fully thermal, right? This is something else, and we will see what it is. Okay, any other question?
Is this entropy per site or total?
No, this is total. This is total entropy, I think, yeah.
0.5 depends on the size. So
Yes. So this was for some small spin chain, maybe 12 or 14, right? But these guys studied the dependence on the system size, and you find that it is linear in system size.
So it means that there is some universal value of the energy density, right?
For given disorder strength, yes. But it is dependent on the disorder strength. Yeah. And in a second we'll understand all of this. How various things depend on the disorder strengths and
Yeah, I guess just to follow up Vlad's question, I mean, so if you took temperature given by the sort of average energy of this initial state, what would this value of S mean? So
wait, say it again. So energy given.
If you took a thermal state,
Yes.
some entropy, for the temperature which corresponds to this energy of whatever your initial state, what value of S?
Here it would be something like 3 or 4. So it's much larger, yeah. Because effectively this is an infinite temperature state, right? Because it has a lot of energy, right? Yeah. Uh-huh.
So you have two sides, right? But left and right.
Yeah.
What do you talk about
Huh?
system size? When we say system size, the total system size.
It's total. You split them equally. So, but this is not really essential. So you could split them non-equally, and you'll still find this log entanglement. Moreover, I think even if you split it, you pick out a few spins, right? And then you say you declare this to be your, well, not left part, but region A entanglement of which you're calculating, right? That would also show slow growth of entanglement, and it would be extensive. So let's now see why the systems are integrable. And so I will just give you an intuition of how this integrability comes about. So let's go back to our random field XXZ spin chain, and for a second, let's make it completely trivial. So let's just keep SZ terms in it, right? So we, for a second, forgot about flip-flop terms. Then, eigenstates are just product states of up and down spins, eigenstates of each SZ operator, and they have random energies because I have randomness in the local field. Now, let me put back flip-flop terms. And then what happens effectively, right? So since you have randomness, typically you would not find resonances, right? So to go from product states to true eigenstates, what you need to do, right? You need to make local unity transformations, right? Which, let's say, admix to this spin, they admix a little bit of flipped spins, right? And so on, right? And so the picture, right, is that you can connect your true eigenstates to the product states by quasi-local unitary transformations, right? So this also has a very simple and intuitive interpretation in terms of perturbation theory, right? So what you do, you start, if you wanted to make it rigorous, right? What you would do, you would say, okay, so let me make a unitary transformation which gets rid of the coupling between these two spins, right? And typically there is no resonance. So I just have to add a small admixture of this state, for example, right? Now, transformations which eliminate flip-flop terms between nearest neighbor spins, right? They would not commute. So you would generate, they would be close to unity, but they would not commute. So they would generate 3 spin terms, right? And so on, and then you continue this procedure, right? And really localization is the statement that this procedure is convergent, right? That there are no resonances. And so your perturbation parameter is effectively flip-flop amplitude divided by disorder strength. Yeah? So this is how one should think about it. Huh? So okay, so you can diagonalize your Hamiltonian with a sequence of quasi-local unitaries. So what good is it? So okay, so one consequence is that you can define a set of local integrals of motion. Because, so let me call this unitary U, right? And it makes Hamiltonian diagonal in the SZ basis. So then you see that H diagonal commutes with each SZ operator. Therefore, if I dress SZ with operator U and call it tau, right? This would commute with a true Hamiltonian, right? And moreover, so what is important? So of course I can define this integral of motion always, but what is special here is that this operator would be quasi-local because it is obtained from a local operator SZ by this local unitary, right? So it's local, so it means that it can strongly affect spins in some volume xi, and it would do nothing to the remote spins, right? So it would have exponentially decaying tails. So and now I can define in fact a complete set of these integrals of motion, right? Because for every site I can define one. And you can easily see that they would commute with both Hamiltonian and with each other, right? And so you can call them effective spins, and they form a complete set of integrals of motion in the sense that if I specify the values of these integrals of motion, I uniquely specify the eigenstate. Yeah.
So this set is specified for each realization of the disorder, right? So you have a standardization of disorder, then you get to a U, and then you can start this stuff, right?
Yes, exactly. So, important thing is that if you deform your disorder potential or you change your Hamiltonian a little bit, you can deform, so this set still exists, right? So from that point of view, many-body localization, it's a phase, it's not a point, right, in the phase space. It's not like beta ansatz integrable systems, right, which have integrals of motion, but they're presumably not robust under generic perturbation of the Hamiltonian. So these guys are robust, right? So okay, so now let's try to use it to say something about dynamics. And first of all, it is useful to write the Hamiltonian in terms of this tau operator, this integrals of motion. And since the Hamiltonian only depends on tau, so since it commutes with tau z's, it can only depend on tau z's, but not on tau x and tau y. Right? So the most general form you can write is this sum of tau z operators and their products with different coefficients. And again, so since this is obtained from a local Hamiltonian with quasi-local unitaries, right, the remote interactions would decay exponentially, right, because these operators are quasi-local, right? Because you know that, yeah.
All these statements can be made only for strong disorder. They actually cannot be made for weak disorder. Is that right?
No, as long as you're in the localized phase, you can define this, of course. Question is, of course, they would probably localization length would fluctuate a lot state to state, right? But formally you can formally this is related, for example, to the following. You could say, okay, let me put a particle, right, in some eigenstate, and let me ask how far does it spread. If it's guaranteed to stay in the vicinity, right, then you can define the integrals of motion.
Right. So this is the same as this usual logic in the localized state that if you want to have the degenerate to degenerate state, they will be very far apart.
Yes.
Energy, the farther they apart in the real space, and that's enough for you to do this.
Not exactly. This problem is more complicated, right? Because here, if you make some perturbation, right, you could couple to exponentially many states, right? It's not just overlap of two single particle wave functions, right? You could, because it's an interacting system, you could create electron-hole pair and more, right? And there are exponentially many possibilities But the statement is that still, right, if interactions are weak enough, even those processes would not lead to resonances, right? You know, in a sense, single particle localization is easy because it's a competition of exponential with the power law, right? Right, because so you have exponential tails of wave functions and level spacing, which decays as a power law in the system size. Here's a competition of exponential with exponential.
I can ask this question in an even more vague way, but I don't know.
That would help. That would help if you get more vague.
You'll see. So people like Efros and Shklovsky, they've been treating interaction in localized states for decades, right?
For ground states. No, not for excited states. No. What they do, they have a ground state and they say, okay, let's excite a particle hole pair here or something, right? It's very different problem. That their phase space doesn't grow as fast. Yes.
How is that very different?
Because here we are talking about highly excited states, right? So here we are saying, okay, so create, extensively many electron hole pairs. And they're all interacting and you ask whether it can lead to delocalization or not, right? No, all the activity was about ground state and near ground state dynamics. So it's not, it's not enough to say that, this pair would not resonate with this one far away. Right? You really need to say, okay, if I create an avalanche of electron hole pairs, right, it still would not lead to resonances. This is the essence of the problem. But okay, so we have this. Let's go back to this Hamiltonian, right? So you have essentially classical spins interacting with exponential decaying interactions. And so picture of this phase is that you can define a set of quantum bits which have infinite lifetime. They can never relax, right? But because they're still interacting, they can dephase, right? And that's what gives rise to non-trivial dynamics. And so, let me now use this to explain this log growth of entanglement and make some experimentally testable prediction. So let's go back to our setup, right? So you start in a product state and you evolve it. Then, so because I have this weak interactions between effective spins, so spins some distance x away interact exponentially weakly, but after exponentially long time, this interaction would give rise to large phases, which would lead to entanglement, right? So dephasing time or entangling time of two spins goes as exponential of this distance, and from that you immediately get that x is log t, right? This is the volume in which degrees of freedom got entangled after time t. And since in general, any state you would prepare would involve extensively many eigenstates, you get that entanglement proportional to log t. And prefactor would be set in particular by the structure of your initial state, right? How many eigenstates it involves. Anton?
Isn't it only true that the entanglement would go to some large quantity if the initial spins, so for a particular pair of two eigenstates closest to each other? Because if this spin interacts stronger with something else, they will become entangled first, etc.
This is a very good question. So that's true, but then there are three spin interactions which would entangle all of them, right? But there is separation of scales. You're right that if it were so you're referring to something like entanglement monogamy or something like that, right?
Well, yes. In one way or in another way, if I have three terms in the Hamiltonian and one is much larger than the other, then I need to rediagonalize it, and the eigenstates will be large.
No. Yes. Okay, here it's not like that, right? Here Hamiltonian I showed, that's already in terms of eigenstates, right? So now it's just about phases, right? No, but you're right. So this proceeds. So you are right, but in a different sense, right? So it's it doesn't apply to entanglement, because for entanglement it's now just about phases, right? And I just generate random phases, and then you just essentially go to the diagonal ensemble, right? All the phases get kind of scrambled. But you are right that if I go back to this picture of how we convince ourselves there are integrals of motion, right? In some places I would get resonances. And those places I have to treat non-perturbatively, right? I just have to diagonalize them and then make sure they don't propagate. Yeah. So this is important. So
The answer is they don't propagate, or so.
The answer is resonances don't propagate. So there are you would have isolated resonances, right?
Yeah.
But they don't couple,
Okay.
right? So they don't lead to delocalization.
Okay.
So, and okay, at long times here we would end up in a steady non-thermal state, right? Which of course, so it retains memory of initial state because you have local conservation laws. But system still equilibrates, right? It doesn't thermalize, but it equilibrates. And one way to see it is to look at local observables. And so I won't go into details, but the answer is that if you do this quench experiment and look at some local observable, it would relax to a steady value, right? Which is non-universal. It really depends on how your initial state was prepared. But this approach would be a power law approach, right? So that's another thing one could test, and I think in cold atoms experiments this would be the next thing to study relaxation of local observables, right? And power law relaxation is a signature of many-body localization. Now, of course, so one could argue that there are many ways in which I can get power law relaxation of observables. If I look at density relaxation, it's also power law. But there are also you can upgrade the setup and do some version of spin echo to really show that you have dephasing in your system, measure its rate, right? That it's really dephasing and not motion of things which gives rise to equilibration. Yeah, it is.
What is the power?
Power, yes, English. So power depends on the localization length and on how your state is prepared.
I see. It's special to every state.
Yes. Well, I mean, of course, statistically, it would fluctuate only a little bit if you fix energy density, right? But it's not it's not pi over E or anything like that. So okay, so let me summarize first part, right? Should I stop or can I take? Well, so what we saw is that MBL phase is robustly integrable, and it has universal dynamics, right? So which can be seen experimentally in the power law relaxation of local observables, right? 2 minutes, okay, good. Thank you. You're very generous. So now let me switch gears and talk about driven systems. But since we spent a lot of time on the first part, we'll have to go fast. So people are interested in driven systems partially because driving gives you a way to modify properties of your system, and as Mark told us, even engineer states which you cannot get in static systems. And there are already experiments. So, for example, here is a paper from Bloch group, right? So where they realize churn bands in driven optical lattices, and this is, this is Emanuel Bloch, right? So very, setup looks very compact. So this is kind of a glamour shot, going out on Friday night, and this is what really it looks like. So this is, without makeup on, in the morning. So driving is really a very useful tool, and there are also a lot of interesting theory ideas how to use driving to realize topological insulators, fractional Chern insulators, so very interesting phase that Mark described. Now, theory is mostly so far limited to single particle systems. So, and we would like to understand what happens in driven many-body systems a little bit. So, what is the intuitive expectation? So, intuitive expectation is that if you have an interacting system and you drive it, it would just heat up to an infinite temperature eventually, right? So it becomes featureless, featureless and boring. But what we want to ask is, so is this the fate of all driven systems? Can some systems not absorb heat and get essentially localized in the energy space, right? And behave as if they had an effective Hamiltonian. And so turns out that this doesn't have to be the fate of all systems. So if you drive an MBL system sufficiently fast, it would not heat up, right? So it maintains its character, it stays many-body localized. And second, you can ask how rapid is heating in driven ergodic systems, right? And let me restrict myself to systems on a lattice, like a spin system. And turns out that you can prove a theorem that at fast driving, heating is exponentially slow in driving frequency. So what do usually people do when they encounter a driven many-body system? So really the only available theoretical tool is Magnus expansion. So what you do, you have your Hamiltonian, you have Floquet operator, which is evolution over one period, and then you try to rewrite it as a single effective Hamiltonian, and you do expansion in 1 over frequency, right? So this is well known. It's a pretty ugly. It becomes pretty ugly at high orders. And presumably it's supposed to give you effective time-independent Hamiltonian. Of course, this cannot be right in a many-body system because this would mean that it does not really heat up. It still has conservation of this new effective Hamiltonian, right? I mean, okay, so you generally cannot have a local effective Hamiltonian, right? And indeed, so Magnus expansion only converges for bounded Hamiltonians, like a finite dimensional system, right? And it would break down in many-body systems because of the heating. So one has to come up with something else. And since I have to go fast, so I'll just try to give you a very quick feel of what you can do. So first of all, to develop some intuition, so one can use the trick that people came up with for kick-trotter. You can adapt it for many-body systems. And so the trick is the following. So the trick is that you can map the problem of finding Floquet eigenstates onto a hopping problem, effective hopping problem in the Hilbert space, where sites are eigenstates of your original Hamiltonian, and hops are given by the driving. So this is how you can map kick-trotter onto Anderson localization. But you can also apply it to many-body systems, and then you develop useful intuition right away. So let's consider first a toy problem. So you have a spin chain, and you drive it locally. So you kick one spin with some frequency, right? Then so you have your Floquet operator, and then just like for kick-trotter, you can map it onto a hopping problem in the Hilbert space. So you have sites which are eigenstates of your original Hamiltonian, and hopping would connect them somehow. And from this, what you see right away is that ergodic and MBL systems respond very differently to driving. So, effective level spacing behaves the same. It's exponentially small in system size, but hopping is essentially set by matrix elements of this operator V between eigenstates. And for the ergodic systems from the ETH, you find that hopping is much greater than level spacing. So there are lots of resonances and delocalization, right? So this is why heating happens in ergodic systems. So now in the MBL system, it's not like that, right? So from this picture of integrals of motion, you can derive how the matrix elements of local operators decay typically, right? And you find that in this case there are no resonances, right? So your system stays localized. Question?
So you could have this system given these interactions to this effective coping model, right?
Yes. But you see, there is a trick here, right? Because so I consider kick only with a single spin, and that gives me a bounded operator, right? This mapping is not nearly as useful for global kick, right, or global driving, because then you have an unbounded operator and it's hard to analyze. Here, you know, for free, I just got a problem in which energies are tangents of original energies, right? And hopping is just matrix elements of some local operator, right? And that problem I know how to treat, right? No. This is general. This is general.
This one is something more about that.
Huh?
It has more degrees of freedom, right? So you still can generalize that.
You can, yeah. So, but if you have a global driving, you have to do something else. But okay, so now I'm really running out of time, and Alex looks stern as sterner than ever. So let me just state two results, and then I'll be happy to tell you details afterwards if you're curious. So first, what about heating rate? Right, so you can prove the following theorem. So you can prove that if you have a lattice many-body system and you drive it with the sum of local terms, then heating rate is less than some constant exponential minus driving frequency divided by norm of HI is essentially, it's a typical scale of your Hamiltonian. So it's either interaction or hopping. Right? So this is a theorem which really follows from the locality of quantum dynamics. And you can prove it for both local driving and global driving. So it holds for any initial states and for strong interactions. So it's not perturbative in interactions. This statement is perturbative in driving strength. It's a golden rule result, but you can make it also non-perturbative in the driving, turns out. But there is no time to talk about it. But this result is completely non-perturbative. If you drive a system fast, strongly, whatever, it still heats up slowly. Driving strength. Driving strength is smaller than the driving frequency. Okay, yes, that's the only requirement. Yeah. Mm-hmm. Because otherwise it's just otherwise you can heat up very fast. Yeah. So and second result is that if you drive a many-body localized system, there is a transition as a function of frequency. So at high frequency it stays localized, it does not absorb heat, it has an effective quasi-local Fourier Hamiltonian which is itself many-body localized, but at lower frequency you're guaranteed to delocalize. And so in the way, so to prove that it's indeed localized at high frequency, so you need to do something different from Magnus expansion, which explicitly takes into account that you have few resonances. Essentially, you need to have a procedure which explicitly takes the spectral properties of your system into account. And you can do that. So you can come up with an iterative procedure which does exactly that and show that it converges if driving is fast enough. Right? So here you get true localization, not just slow heating, but true localization. Right? So last thing, there have been some works which claimed energy localization in periodically driven translation invariant systems. But you know, this was done really based only on short-time numerics, right? And there is no theory of it. So, and here just a little warning, right? This result shows that it's very easy to get slow heating, right? So it's very easy to confuse slow heating with true localization if you're not careful. And I think that's what happened in these models, right? So my guess is that, you know, this is the explanation for what this paper's observed. So okay, so I will stop here. Sorry for running over time, and if there are any more questions.